of those issues. Okay, it looks like we are now recording, and I'm going to share PyCharm, and I also need to share Chrome, and we'll start with those. Okay, so getting down to the end of the semester. 2 more lectures after this one, then the final. So let's get started. I need to add something to this. Administrative notes. I am being reminded by university management that I am supposed to have you fill out a course evaluation of me for this course. Please do so if you have not already done. I apologize for not having warned you about that. Fortunately, this is not in the old days when I used to teach at UMBC, where I had to pass out forms to designate somebody to pick them up, and then I had to leave the room for 15 minutes in the middle of the class and all this other stuff. You actually do, excuse me, have a chance to provide constructive feedback. And being blunt, there have been times in the past when students have given me very constructive feedback on how to make things better for future students, what to try, what not to do again. What have you. So, you know, go ahead, take your time. Won't take you but a couple of minutes and try to be constructive. And constructive doesn't necessarily mean positive or negative. Negative is valid. You know, again, it's been an interesting school year. I know you didn't come to UMBC to enroll in an online degree program, but we're doing the best we can to get you through. So that's the first thing, get your course evaluation done. The final is the 17th, that Monday, 2 weeks. It's scheduled 3:30 to 5:30 on Blackboard. Now, I've already got a couple of students who, for valid reasons, just can't take it during that time period. Okay. So if you have a problem during that time period, let me know. We can, I mean, it's on Blackboard, so we can arrange it at any time. My concern is me being around if a question isn't clear, if you need to ask a question or something. You know, I'm guaranteed to be there that 3:30 to 5:30 time period. I'm actually attending the biggest cybersecurity conference in the country. The RSA conference is all virtual this year. And so I'm actually attending that conference online. So I will be monitoring during the entire exam. As I said, I've got a couple of students who can't make it, so I'm also planning on offering it that Monday, the 17th, from 8:30 to 10:30 a.m. for you morning people. So anybody else who wants to, you know, if you're a morning person and you want to take the exam 8:30 to 10:30 that Monday instead of in the afternoon, that's fine. Just let me know. I will make sure Blackboard makes it available for you. And again, the difference is I'll be around. If nothing on that Monday works and we have to do it some other time for you, you know, the big issue is making sure I can answer a question. I'd hate to have you submit a final exam where you said, gee, programming assignment number 3 wasn't clear. I didn't understand what you wanted, so I guessed. Yeah, well, let's have it when I'm around. So if you do want to take it at a different time, let me know. Like I said, I'm definitely going to be online that morning, and I'm going to be around during the time it's offered. If I need to do it something else, we'll let you know. Project 3, 1 week from today. As I mentioned on Monday, you should have major parts of it working by now. You should be able to at least read in one file. Hopefully, based on what we talked about Monday, you can read in all the files now and create your master database, your whole list of all the data. And then the next step is just minimizing. It's just, you know, creating a new 2D list with only the columns you want to keep in it. That's fairly straightforward. You should be there now. If you're not to pandas, if you're not to drawing graphs with Plot9, that's okay. Gotta wait. But you should be up to the point where you're creating this big honking 2D list of all the data. If not, you know, you probably need to get help. Since we are doing a different project 3 than the majors are, the majors TAs may or may not be able to help you. They can help you with Python questions, but they, you know, they're not TAing the same assignment. So Kevin and Mariah would be your go-to sources in addition to me if you're having issues. Please do not wait until, you know, Monday night the 10th or Tuesday morning the 11th to really figure out what a Jupyter Notebook is, because it's going to be an issue. We are hopefully at the end of the day going to talk about graphing, and you're going to see me Building a plane while it's flying is the old joke. What that means is I'm going to try to demonstrate how to use Plot9, having not prepped anything, so we'll see how well it works. You will, at a minimum, see the common mistakes that you recover from, but we'll do that. Homework 6 is out. It's pretty easy. It's due next Monday. This is what I needed to add. Just get it done. I know a couple of you actually got it done before I had the submission open. That's awesome. I like that. That's good. You must submit, if you read the assignment, 6 files. There's going to be 6 different files you have to submit. Part 1.py, and it helps if I can spell. Part 2.py and part 3.py are the code. Kevin and Mariah need to see your code so they can make sure, that you're not fudging anything, you've done it legitimately. And the results files, which I told you in the assignment to call part 1.results, part 2.results, and part 3.results. These are the actual graphs that your program will produce. The problem with gl.umbc.edu is a Linux machine. It doesn't, there are Linux windowing systems, but for whatever reason, we don't run a windowing system on it. So if you try to execute, for example, part 1.py on gl.umbc.edu, it's going to give you an error message and tell you it can't create a screen on the window to draw in. So that's why you have to provide the results so that they can validate it. The code is fairly short. This is nothing hard. This is nothing complex. It's just a chance for you to play around with something that isn't text. It's due Monday night, the 10th. Let's get stuff done. So those are the administrative notes that we needed to get behind us. Homework 6, project 3, and then, of course, gets to the final. We got 2 weeks. All right. So now we want to get into, as I've said, something that really follows last Wednesday's lecture. And the reason it doesn't immediately follow Wednesday is because I really wanted to do a detour on Monday to get you going on project 3. But this follows last Wednesday's lecture. And you'll see that when we get into PyCharm. This is an analysis of algorithms. Okay. We covered 2 ways to do searching on Wednesday. Linear search, where you just take a list and you look at every single item until you either find what you're looking for or you determine that what you're looking for is not there, and then you stop. Okay. And we covered 3 different sorting algorithms. Bubble sort, where you bubble the biggest item to the end every time. Selection, where you select the smallest item and put it in the first element every time. And quick sort, where you split the list into 3 parts. You pick a pivot at random, you split the list into 3 parts, those that are less, those that are greater, and those that are equal, and then you recursively call it again. And I mentioned a little bit last Wednesday, I dropped some hints into this lecture, and now we're going to talk about how computer scientists classify algorithms and what we mean in terms of speed. Okay? I have a 120 element list here, L, which is created by calling random.randint, and I just generated 120 integers between 0 and 100 inclusive at random and threw them into a list because I wanted something random that wasn't sorted. So this list right here, L, is the length is the list that we're going to sort. We're going to sort and then we're going to search for it. Okay. Just to show you that it really is, I run this and it does print out that there are 120 elements in the list. Nothing up my sleeve. I'm not doing anything fake. This line doesn't do anything. Now, since this follows on from last Wednesday, what I did is I simply imported last Wednesday's module. Okay. As a reminder, this is April 28th coding, the in-class coding for last Wednesday. I did an iterative version of bubble sort. I did an iterative version of recursive. Let's try this in English. I did a recursive version of bubble sort. I did an iterative version of selection sort and then a recursive one. And then I did quick sort, and you can do it iteratively, but it really only makes sense recursive. I modified these a little bit, but not a lot. All I did was make the comparisons just a little bit more efficient. But let's walk through what bubble sort does. I inserted some stuff that I only talked about a little bit last time. I'm going to count. Remember, at bubble sort, we go through and comparing two elements, and if the left one is smaller than the right one, we leave them the same, and if the left one is bigger than the right one, we swap them. Where left and right means earlier in the list and later in the list. So what I'm going to do is I'm going to keep track of how many comparisons I have. I'm going to keep track of how many times I swap elements. I start out this is how I'm going to stop I mentioned that with bubble sort, you can tune it. You could, if you've gone through a list and there are no swaps made, you have not swapped anything, you can stop you can short circuit the process. You can stop the bubble sort. You don't have to go through anymore. You're done. Okay, can't do that with selection sort, but with bubble sort, you can track, and if you haven't swapped anything on a particular iteration of through the list, then you can stop. The code here is actually a little bit of an optimization. It's a little bit better than the one I gave you on Wednesday, so we used it, but it's essentially the same thing. I use a while loop instead of 2 for loops. Okay, last Wednesday's code used two nested for loops. This time I'm going to use a while and a for. It makes it a little nicer. Not a big deal. But at any rate, what I'm going to do is I'm just going to go through. Remember, the biggest integers each time through get put in the last space in the list. It bubbles its way to the top. It bubbles its way to the end. And so now I'm done with that last element, and every time through the list, I go one fewer times. I go one fewer time through the list each, and that's what this is controlling, is it tells me how many times I go through. Okay. Every comparison I do, I add 1 to my number of comparisons. And now, if the left number is bigger than the right number, I have to swap. And so I add 1 to my number of swaps. And to control my whether or not I've swapped, whether I'm going to short circuit the list, I have this Boolean. It's just a Boolean flag while loop's all it is. Okay. The main things I'm going to count are, I start with comparisons are 0. I start with swaps are 0. Every time I make a comparison, I add 1. Every time I make a swap, I add 1. This number of iterations just keeps me track, and that makes sure I don't compare the end of the list. The end of the list is already properly sorted, no point in saying it. Then I print out how many comparisons and swaps I had, and I return. So, import April 28th coding, get my randomly generated list L, okay, and now just print out the length. You can see it's 120 elements, nothing up my sleeve. What I'm going to do is I'm going to print out the sorted list. You can see that it has indeed been sorted, and this call to the function will cause that other print statement to execute that tells me how many swaps and how many comparisons. Remember that since I imported this file this way using this statement, I have to tell Python I want you to use iterative bubble sort from April 28th.coding. There may be some other iterative bubble sort somewhere, and Python will get confused. So I'm going to say, take that module I imported, my own code, use the iterative bubble sort in that module, and sort the list L, which is defined up above. Okay, since I'm not going to do everything here, I'm going to run a Python console to do this. I'll run the whole code just flat out later on. So I'll copy and paste my 4 statements here. And let's go. It got confused because the Python coding is a different variable. Apologies for the phone. Let me shut that off. Okay. Sorry for the phone. All right, we'll do it this way. This file is called May 5th coding. Here we go. Ignore this part. We're not going to get there yet. When I ran the code, May 5th coding, so that it properly imported. What happens, the reason the Python console gave me the error on the import statement is because the Python console starts in a different directory. It's a different working directory than when you run. And so I would need to put the entire path name there, which I can do, but that's okay. This is the result. This 120 is the result of print length L. And now the call to April 28th coding iterative bubble sort of L caused this statement to be printed. There were 7,074 comparisons and 4,010 swaps made by bubble sort in terms of sorting the list, right? And here is my sorted list, and you can verify if you go through it that it is indeed a sorted list. Okay. Now, that's not bad in terms of how long it took and how many comparisons and things like that. We'll take that. Let's remember something. Remember what's interesting about lists and dictionaries, among other things, is that they are mutable. Because lists are mutable, when I called April 28th coding dot iterative bubble sort, when I called iterative bubble sort on this, okay, it actually modified because I did not do a deep copy. If you look back here at April 28th coding, I did not do a deep copy of the parameter. This function was operating on the same locations in memory as what was called. So right now, this list, as you can see right here, is sorted. So what if we immediately ran that function again? So understand that right now, what I'm doing, and I'm going to comment out, I jumped ahead of myself with the Python code. And I'll come back to that later. Let's just run this. Now, looks what happens here. Print length of L, that's to show you where we are. There's a list of 120 elements. The first time through the list, this is the value of L. It is this random list of numbers. So to sort that, it took 7,074 comparisons and 4,010 swaps. Now, remembering, as I said, because this is going to illustrate two things, lists are mutable. So this function operated on these exact locations in memory, and this function therefore changed the value of L. So when I said print L, this is the result of print L. And you can see that it is indeed a sorted list. So to remember, when you pass a list to a function, the function is going to change the value of that list unless you have made a deep copy. So you have to remember that. I cannot tell you the number of times I've looked at a program going, what the blankety blank blank just happened to that one? Why did I get the error? And the answer immediately comes to me because I passed the list. I didn't make a deep copy. Lists are mutable. And so I have now changed my original data. And so, of course, it doesn't work right. That's what happens here. The other thing to remember is that when I immediately called this a second time, okay, same function, doing the same thing, doing a bubble sort, it was passed the sorted list. So this is the list that was passed to this function call. Now, the first time through the list, because it is sorted, it is already in order, there are no swaps made. And so the function stopped. The function said, I ran through a 120 element list one time. That means I made 119 comparisons, and I made 0 swaps. Everything was in order. You passed me a list. I don't know why you wanted me to sort a list that was already sorted, but you did. And so I very efficiently told you it was already sorted and we're done. So a random list, a list that was randomly generated of 120 elements, took 7,000 comparisons and 4,000 swaps to sort it using bubble, whereas one that was already perfectly sorted took 119 comparisons and 0 swaps. What does that mean? We're skipping the search in the slides. I am going to come back to that. In computer science, we use a notation called big O, and it is simply a capital O. Big O notation, capital O, stands for on the order of. This is what we use to say how fast an algorithm takes. Any given algorithm to solve a problem has an order, a big O of something. Often, not always, but often, it takes some number of operations, some amount of time that is a function of the number of elements you're dealing with, the amount of data you're dealing with, the number of elements in a list. If we are sorting a list, we talk about an algorithm being able to sort in some function of the number of elements in the list, n. So, normally we assume we're dealing with a list of size n, and so the algorithm is some function of n. Well, it turns out that, jump ahead to a slide, bubble sort, if you have a list of n elements long, in the absolute worst case, you have to go through all remaining unsorted elements of the list. So the first time you have to go through n elements, 120 in our case. The second time you have to go through 119. After the first time, you know the last element's the biggest, so no point in looking at it. So you have to go through 120 elements the first time, 119 the second time. Now you know the top 2 are in order, so you only have to go through 118, 117, and so on. Generically, from math, you should have learned way back in the ancient days. I got this in calculus. I suspect you probably got it in algebra these days. But we know that the sum of the numbers, I can't make a big sigma, I'd have to find it, but the big sigma, the summation sign of I from 1 to n, the sum of the first n numbers is equal to n times n minus 1 divided by 2. That's where this comes. That's what this statement comes from, is it comes from here. We know from like I said, I got it in calculus, you probably got it in algebra, that's fine, that the sum of the first n integers is n times n minus 1 over 2. So therefore, in the worst case, if I have the worst possible case, I cannot stop bubble sort early. It takes approximately n times n minus 1 over 2. Well, n times n minus 1 over 2 is n squared minus n over 2. I just multiplied out the n. Okay, so I get n squared minus n over 2. Now, we round this off to n squared, and I'll show you why in a minute. Okay, we don't say it's bubble sort is O of n squared minus n. We just say it's O of n squared. So if you're asked to describe the bubble sort algorithm, bubble sort is O of n squared. It takes on the order of n squared operations to sort a list of length n. That's your computer science, hardcore comp sci 411 analysis task, right? Actually, 341 gets into it a lot. Okay. How long does it take an algorithm to run? It takes O of n squared. On the order of n squared operations if you have a list of length n. Now this is, remember O, this is the worst case behavior. And a lot of times you want to know the worst case because you want to make sure your program isn't going to crash in the worst possible case. If you can work efficiently in the worst case, then you can work pretty well in all cases and you're good. Now, there was another term on the previous slide that I skipped that we'll get to now, and that is omega. We talk about the worst case because that is generally important, but sometimes we care about the best possible case. What is the best possible case of bubble sort? Well, the best possible case of bubble sort is this one right here. If you hand bubble sort a list that is already sorted, it's going to run through the list one time. It's not going to do any swaps. And so it takes on the order of n operations, basically 120 lists, 120 element list. It took 119 comparisons. That's pretty darn close. That's on the order of n. And so we signify that by the Greek letter capital omega. We say bubble sort is omega of n. If the list is already sorted and you stop when you don't swap anything, you only have to go through the list once and we're good. So bubble sort, the worst possible case for bubble sort is O of n squared. It's the worst thing we can get. The best possible case, it's omega of n. Now, somewhere I've got it on a slide. I'll do it now because I probably got something important somewhere that I'll lose. Why do we round off? I mean, 120, right? 120 element list. Well, 120 squared is 14,400. So 14,400 minus 120 divided by 2 is, what's that, 14,280, 7140. So it makes a big difference, you know, 120, 7140 is not really all that close. It would seem like that's kind of a misleading number. We need to know that. But consider a data set n is 1,000,000. Now, I very foolishly, the first semester I taught this class using this Mac, which would have been fall of 2019, 3 semesters ago, I very foolishly started the computer in front of class in Meyerhoff 030, the big chemistry auditorium, with 105 students in my class and said, let's see how long it takes to sort an element of a list of 1,000,000 random elements. The answer is it will not finish during a 75-minute class. Don't do that. I wound up killing it after about 5 minutes when I realized that this was a foolish idea. But in real life, you might have that, right? You may be asked, 1,000,000 is small. In my data science program of a couple of years ago, where I got my most recent master's degree, right, we dealt with some Twitter feeds where we were literally getting billions. We were getting billions of tweets put into the Amazon cloud that we were having to sort through, right? But even 1,000,000, n squared is 1,000,000,000,000. Now, 1,000,000,000,000 minus 1,000,000, that's really close to 1,000,000,000,000, right? That's 999,999,000,000. For all intents and purposes, we'll call that a trillion. And yeah, I have to divide by 2, but even then, I'm even dividing by half a trillion, or dividing by 2. And so since we're dealing with on the order of things, we're going to say that's close enough. Round to 1 trillion. Okay, this is why we round to n squared. We round to n squared because when we're dealing with big numbers, when we're dealing with million element lists or billion element lists or anything like that, we're dealing with numbers so high that n squared minus n is essentially n squared. 999 billion, 999 million is real close to a trillion for any purpose I ever care about. Okay, and then even dividing by 2, it's not that big a deal. So the bottom line is we round off when we're calculating O and omega, but mostly O. We round off and we just say bubble sort is O of n squared. In the worst case, it takes the n squared operations. In the best case, it's omega of n. Okay, so that is how we describe algorithms. And that's important because now somebody asks you, well, would you like to use this cool new algorithm? And you say, what's its order? What's its big O? And they say, it's a really cool algorithm and it's only an order of n cubed. It's O of n cubed. You go, holy crap, 1,000,000 cubed? That's a quintillion. I haven't got that kind of computer power. No, I don't want to use your algorithm. That always happens when somebody, in cybersecurity, somebody has a great new way to decrypt your RSA key. I can break this and find the RSA encryption key, and you can read it and break into the system. What's your algorithm? Oh, it's O of n to the 10th. No. Okay, I haven't got that kind of computer power on the planet. So you know up front that this is a useful quantity. All right, now, this is where I had it. Don't sweat the small stuff. Don't sweat the small stuff. It's exactly what I just derived it for you. You just saw me drive it instead of here. It's here. Bottom line, just round off. Now, selection sort. Okay, let's go back to pie chart. The two big things about selection sort, let me delete these comments. The two big things about selection sort are, number one, you make fewer swaps than bubble sort, right? You only swap one number at a time. Where am I? Iterative selection sort. Here we are. The only time you swap is the latest number you found with the smallest. Okay, you're looking for the smallest, so there's not a lot of swap. You're not swapping every pair of numbers. So selection sort seems interesting and better than bubble sort because you do fewer selections, fewer swaps. But you cannot short circuit selection sort. You cannot stop early if the list is perfectly sorted, and we're going to prove that in a minute. Okay, so let's go back to the May 5th, today's coding. Now, remember that lists are mutable. Right now, this list L is the perfectly sorted in order list. I don't want to deal with that, so I'm going to reset. Again, I could have solved this by making a deep copy, but just to do quick and dirty, I'm going to reset to my original random list. This is just here. I just recopied the random list. I reset it. So now I'm making a fair comparison between this first statement. Okay. I'm going to comment out this, and I'm going to comment out this because I don't need that anymore. I reset my list, and now I've got to do a fair comparison between iterative selection sort and iterative bubble sort, and I'm sorting the identical list, so it's a fair comparison. Let's run that. Okay, here are our results. Again, this is just print the length of the L. You can see I've got 120 element list. This is bubble sort with the random list. 7,074 comparisons, 4,010 swaps. Okay. Iterative selection sort, 7,140 comparisons, 120 swaps. 120 versus 4,010. Iterative selection sort, by the way, the recursive numbers are on the same order. Recursion does not change the order of the algorithm. It runs about the same. Okay. 120 versus 4,010. So selection sort looks interesting because I've got a lot fewer swaps. And 7,074 comparisons versus 7,140 comparisons. That's almost the same, right? Now, I'm going to show you two more things, but first I'm going to show you an interesting thing. Note, I import April 28th coding. If I make a change to April 28th coding, the next time I run this program, it's going to be, that change is going to be reflected. So if you notice, I made a minor error when I printed out, when I wrote my print statement. I told you how many comparisons, but I left out the word comparisons. So let's fix my print statement. Now, I just changed April 28th coding. It is imported in May 28th. Guess what? Because of the importing, that change is reflected. So, sidetrack importing modules using code. Nice thing. I never have to worry about keeping things consistent. That configuration management. I went back to the original file. I made my error correction. I fixed that print statement. We're good to go. Never had to touch this one. This one never knew that there was a change made in the other program. It was cool. Okay, now getting back to the thing I wanted to talk about here. Okay. Again, lists are mutable. This, after this runs, L is this perfectly sorted list. So let's run selection sort again. Now we will know, and I'll uncomment these. We're going to generate our random list. We're going to run bubble sort on the random list and see what it does. We're going to run bubble sort on the sorted list. We're going to reset our random list. We're going to run selection sort on the random list, and then we're going to run selection sort on the sorted list. Here we go. Nothing up my sleeve, still the list of 120 elements. Bubble sort random list. 7,074 comparisons, 4,010 swaps. It's exactly what we expected before. Sorted list, bubble sort. 119 comparisons, no swaps. Right? Because we short circuited. The list was already sorted. There was no need to do anything. We ran through the list once. We confirmed it's already sorted. We're done. Now, selection sort. We reset random list, sorting the random list selection sort. 7,140 comparisons, 120 swaps. Now, we passed selection sort a sorted list. We gave it a list that was already sorted. The bubble sort was able to short circuit. What did selection sort do with the already sorted list? 7,000 comparisons, 120 swaps. Selection sort is as bad or good, but as bad on already perfectly sorted data as it is on random data. Selection sort has the worst case and the best case as the same. So selection sort instead of bubble. The advantage is you're going to have a lot fewer swaps. The disadvantage is if you already have a sorted list, you're going to waste a lot of time. So again, n squared, if you do the same math, it's exactly the same reason for selection as for bubble. It is O of n squared, worst case, just like bubble. It's O of n squared. And we saw that 7,000 comparisons versus 7,100 comparisons, right? N squared minus n over 2. We told you that n squared minus n over 2, n squared minus n over 2 is around 7,140, and that's pretty darn close to the number of swabs we got. Okay, so that's about right. Sorry, one slide too far. Here we go. So selection sort is O of n squared, but it's best possible case. Selection sort is also omega of n squared. The best case, the worst case, it doesn't matter. Selection sort is the same. It is equally good or equally bad no matter what your input is. Bubble sort can do better sometimes. Now, another term we will introduce is theta, big theta. An algorithm that has an O and an omega that are the same. So selection sort, O, omega are the same. If that is the case, then we define a new value, because we got lots more Greek letters to use, theta. And we say theta of n squared. So only if O and omega are equal, then we say this is theta, and we summarize by saying it's theta of n squared. So when I tell you that selection sort is theta of n squared, you go, aha, theta of n squared means it's O of n squared and it's omega of n squared. Its worst case is n squared, its best case is n squared, it's n squared for everything, and there's nothing we can do. For bubble sort, theta does not exist. There's no such thing as theta of bubble sort. If somebody asks you what's big theta of bubble sort, the answer is it's undefined. It doesn't exist. Why? Because O and omega are not the same. Okay, it's defined. Theta is defined for selection sort. That's just a minor issue. You really want to pay attention to O and omega. Now, quick sort is different. And quick sort, what I'm going to teach you, you're going to find lots of research that's going to give you a different answer, and I'm going to explain why. I use the terminology that UMBC uses in this class for big O, and it's kind of non-standard. So let me work through this and explain. You know from last time, let's look at pie chart, and let's look at April 28th, and let's look at quick sort. Sorry, I looked at the wrong one. Okay. Quick sort is probabilistic. Pick a pivot at random. Now, I told you on Wednesday of last week that my random selection of a pivot was to pick the first element. Okay. It turns out the algorithm works the same no matter which one you pick. So randomly picking the first is as good as you're going to get. So I randomly pick the first element. Then I take the entire list and I split it into 3 sublists. Those that are less, those that are greater, and those that are equal. Okay. And now once I've split the list into those 3 parts, those greater, less, and equal, I call quicksort recursively on the less. I call quicksort recursively on the greater. I don't have to call anything on the equal because I know exactly what it is. It's exactly equal and it's exactly in order. So that's fine. Don't do anything. And my base case in quicksort is if I have a list of 0 or 1 element, it is by definition already sorted. I don't need to do anything. I just return the listed up. So that is my recursive implementation of quicksort. Now, going back to big O, what does this mean? Well, you got to think about big O being absolute worst case behavior. I talked about this a little bit on Wednesday of last week. Suppose that you pick the absolute worst value as your pivot. And by absolute worst value, that means everything is on the same side of the pivot. You pick the lowest value, so nothing is less, nothing is equal, everything is bigger. That is the worst possible pivot you could pick. And since you're picking at random, there's a chance it could happen. It's not a big one, but there's a chance. I mean, 120 element list, the chance of randomly picking the worst possible one out of the 120 is 1 out of 120. Well, but then you're picking a pivot out of 119, right? When you pick that one, the chance you pick the worst out of those 119 is 1 out of 119, and so on. You could pick the worst out of 120, followed by picking the worst out of 119, followed by picking the worst out of 118, followed by picking the worst out of 117. If you do this math, you're going to win Powerball and Mega Millions both many times before you pick the worst case 100 times in a row. But you have to consider it could be the worst case. So in the worst case, we pick the wrong pivot every single time. We will pick the worst possible pivot. Then quicksort is O of n squared. The worst possible case of quicksort is n squared. And that happens if we pick the worst value every single time. Since we're picking at random, we got to be darned unlucky. But it is theoretically possible, so we can't. Now, what you will often see if you Google it is that quicksort is big O of n times the log base 2 of n. Okay. This is, see if I can make that a subscript. Where's the subscript? There we go. Okay. You will often see, and this is the notation I learned when I first started taking analysis of algorithms back in the day. This is what I learned. I learned that quicksort is O of n times the log of n. Log base 2 of n, you just say log of n. Why? That's the more likely average behavior. Okay. If you pick an element as the pivot at random, in general, what you're going to do is you're going to pick about the middle element. You're going to pick one that's probably bigger than half and smaller than half. It's okay. You'll be in the middle. So on the average, what you're going to have is that about half the elements are less and about half the elements are greater. Okay. Let me put a new slide in here. I don't think I have one. I want to explain this. Yeah, I do. I sort of have it. Let me go in more. On the average, you're not going to pick the worst possible. You're going to pick something that's in the middle. Okay. And so you're going to take the list, and what you'll discover is that if the list has n elements, n over 2 will be less, and n over 2 will be greater. So now your recursive call each have n over 2. So round numbers here. My original list has 120 elements. My recursive calls will have 60 and 60. And again, on the average, I'm going to pick a pivot somewhere in the middle. And so each of those are going to have this 60, when I sort 60, I'm going to have 30 greater and 30 less. For this 60 has 30 and 30. Then again, 15 and 15. Right? And now I'm splitting the list. Then either 8 or 7. Let's go with 8 because it's a power of 2. 8 greater, 8 less. Could be 7 and 7. This is 15. Let's make it 7. 7 and 7. Okay, then 3 and 3. Then 2 and 2. Then 1. Okay, and 1 is our base case. We're done. So we can see how many times do we have to make a recursive call? 1, 2, 3, 4, 5, 6, 7, and then the base case. So 7 or 8, roughly. Okay. What's 2 to the 7th power? Okay. Squared is 4, 8, cubed is 8, 4th is 16, 5th is 32, 6th is 64, 2 to the 7th power, 128. Approximately 120. 128 is fairly close. So if it takes about 7 calls, so basically the log base 2 of 120 subscript the log base 2 of 120 is approximately 7. Again, we're rounding off 7, 8, something in that ballpark will be fine. Well, okay, that only gives me part of it. So that gets me the 120, the 60, the 30, the 50. Now I have to keep going the others. There's the other 30, the other 15, the other 7, the other 3, the other 2, and so on. That's where the factor of n comes in. So how many calls does it take? It's going to be approximately log base 2 of n. And then when I add all the recursive calls I've made, that recursive call, that recursive call, that recursive call, that recursive call, and so on, times n recursive calls, that's where you get n times the log of n. So for the purposes of this class, and I try to be very careful you do not get a nasty exam question about this. You can rely on it. Plus, it's open book. You can look it up. In almost every computer science endeavor you undertake, quick sort will be described as on the order of n log n. O of n log n, which is less than O of n squared. You can calculate O of n log n and you can calculate n squared and n log n for various values of n. N log n is always worse, or it's always less. Let's try this again. N times log n for positive integers is always less than n squared. So quick sort is faster. That's why we call it quick sort. That's why we use it a lot. It is the most common sorting algorithm. If you have to implement a sort in a computer program, you will almost always pick quick sort, and this is why, because it is faster. Because in most realistic cases, quick sort is O of n log n, which is much faster than n squared. It's much less than n squared. It's much fewer operations. It runs a heck of a lot faster. But in the absolutely worst case, if you are incredibly unlucky, and you should never in your life buy a lottery ticket because you're that unlucky, the bottom line comes out to be the absolute worst case of quicksort is O of n squared. So anybody taking the majors classes, any of those 500 students are going to tell you that they covered 2 to 3 weeks ago that quicksort is O of n squared. And it is. That is the absolute worst case. You can find a case where it takes n squared operations to run. That involves picking the absolute worst possible element as the pivot every single time, which is not practical. It's not likely. It's not going to happen, but it's there. The best case is omega of n. When is omega of n? Well, if you give it a list where every value is identical. Because remember that we take the list and we split it up into the list of less, the list of greater, and the list of equal. Well, if everything goes into equal, we're pretty much done, right? We're going to make a call on an empty list, which returns 1. Returns the empty list. We're going to make a call on the empty list of greater, which returns the empty list. Actually, it didn't even have to be empty list. We're allowed 1 value there. But if essentially everything in the list is the same value, is equal, then all you had to do was go through the list at one time and put things into this equal thing, and you're done. And so that's why the best case of quicksort, and it's not a list that's already sorted, it's a list where everything's the same value. The best case is omega of n. Come up with a case where everything runs, it's just linear, it's just called linear time, omega of n. Now, so that's our computer science, that's our analysis of algorithms. Going back to what I skipped at the earlier part of the slides. Linear search. Linear search is O of n, and it is what's called omega of 1. Okay, O of n. What is the worst case? The worst case is I am searching for an element in my list that is either the last one or that is not there at all. In that case, I am going to have to look at every single element in the list, starting at the first, then to the second, then to the third, and keep going and keep going. Okay, and so I give you an example. I generated this random list, and I discovered by looking at it that 83 is not in there. I did not generate any 83s. So if I'm going to look for the number 83, I'm going to look at every single value in the list, and then I'm going to say, not there, pal. Sorry, didn't get it. It wasn't there. It is O of n. Its worst case is O of n. I have to look everywhere. What is the best case? The best case is that the first number in the list is the number I'm looking for. Okay, go take this list and find me 22. Found it. So what we say about linear search is that it is O of n. The worst case, it takes the number of elements in the list. I have to compare every single one. So it's O of n. That's its worst case. What is its best case? Omega. Omega is actually omega of 1. It does not matter how many elements are in the list. N does not play into this at all. If I find the value in the first element of the list, it takes 1. So when we describe linear search, we say it is O of n, and it is omega of 1, because in the worst case, I have to look at all n elements in the list. And in the best case, it doesn't matter how many elements are in the list. It doesn't matter if n is a trillion. If I find it the first time, I'm done. 1. Omega of 1, O of n. Binary search, and this slide just explains what I said. Binary search is like quicksort in the sense that we're splitting the list in 2 every time. So we're starting with a list of 120. We're figuring out whether it's left side or right side. Now we got a list of 60. Now we got a list of 30. Now we got a list, and so on. Okay, n log base 2 of n. That is our worst case. With a list of 120, in 8 comparisons, I will know if the element is there or not. I will have either found it and it's not there. So in the worst case, binary search is O, order of log base 2 of n. And log base 2 of n, again, is a lot less than n, always. For positive integers, the log base 2 is always a lot less, right? Thing we just talked about. 2 to the 8th is 256, right? The log of 256 is 8. So just in a simple case, if n is 256, the log base 2 is 8. You can see how much faster. And if n is 1024, the log of 1024 base 2 is 10. So with binary search, we're talking 10 operations, 10 searches. With linear search, we're talking 1024. So if, remember, binary search only works on a sorted list. If your list is sorted, binary search is going to be a lot faster than linear, because with a list of 1024 elements, binary search, 10 looks. 10 searches, absolute worst case. Linear, you might have to look at all 1024. And I tell you, I'd rather look in 10 places for my phone than 1024. Right? A whole lot faster, you're either going to find it or it's gone. The best case, again, binary is just like linear. I may find it in the first place I look. And then it doesn't matter how many elements, doesn't matter how big n is. What you're going to discover is that you found it in the first place. So best case, omega of 1. So that is analysis of algorithms. We'll talk about this a little bit more on Monday, the 10th, okay, which is kind of a course wrap up, and a little bit more I'll talk about. What you need to take from today's lecture is computer scientists study algorithms and how much work is involved in those algorithms running so that they can pick the best one for the situation, okay? Computer scientists will essentially always pick quicksort over bubble selection. Why? Because realistically, n log n is a whole lot less than n squared, and that's what you're going to get almost all the time. There is a degenerate worst case where quicksorts is bad, but it's extremely unlikely to happen. Okay, so computer scientists do this analysis of algorithms and figure out how well they work and don't work. And if you give me a new algorithm to solve an existing problem, you will be rich and famous before next Tuesday and can blow off the final. And if you bring me an algorithm that's of n to the 4th, people will probably thank you and ignore you. It happens. So that's what we're doing here. That is our analysis of algorithms topic, and it follows on to the different algorithms. And as I said, in practice, when you have to sort, you will do quicksort, and when you have to search for something, if at all possible, somebody will sort the list so you can do a binary search rather than linear. Now, since I have, looks like 12 minutes, I want to talk very quickly about the project. There is one thing I want to do. This is the code I ran. So today's lecture's over. This is just talking about Project 3. This is the code I showed you on Monday that reads in all 14 data files on my computer and puts them into a single list. So let's go ahead and run. I called that test for program 3. And we can see that that was how I built a single list. Now, I don't have the dates in this yet. I told you you have to insert the dates in each list, but that's fine. Now, the question is, what do I do next? Okay. In order to run the graphics, you are going to have to use pandas to convert the list to a data frame, and then you can use plot9 to do the graphics. Okay. Pandas is kind of finicky. Certain things are case sensitive. I didn't look at the instructions, but I probably was not case sensitive in the instructions. What I want to make sure is that I've got pandas installed so I can import it. So pip install pandas. Let's make sure that works. Okay. and pip install plot9. That should work. Okay, these are things you have to do in your Jupyter notebook. I was just doing them in here if I can. Now, let's see if this is going to work. Let me import pandas as PD. Why? Just because we almost always do. And let's import plot9. And we'll see if the installs took. Nah, I gotta fix the directory. Hang on. File. New. Virtual environment, etc. Run 3A. This should work. Okay, in a new project. Should pick a new window. Okay, no problem. Creating a new Jupyter notebook. Just takes you a minute. Yeah, it's not going to let me install it's not going to let me open a new notebook until virtual end finishes. Sorry, this will take just a minute. Yeah, man. The problem with this is since I had Jupyter Notebook running in the background because of another project, and I was told to create a new environment, it's disconnecting all of my old Jupyter Notebooks so it can give me a new clean Jupyter Notebook, and hopefully we'll be able to finish this so I can actually demonstrate something for you. Okay, now let's see if we can get this correct. I want to open a new Jupyter Notebook. Let's call it demo.py. It's got to be demo.py notebook. Sorry, it's okay. No problem. Okay, we're going to get started. I want to do import pandas. Okay. As PD. Okay. Now add a new cell from plot9. Import yes. Okay. Let's run these.
Oh, you had a spelling error, Professor.
Oh, okay. Which one?
Like,
yeah. In answer to Lucas' question is any code I gave you, you can use. I'm sorry. Where did I have a spelling error?
like you said, from plotline import as AES, you spelled it like as.
Oh, thank you. Sorry. All right, I have to fix this. Hang on a second. Let me look. Okay, we run these. Let's see. geomline is what's going to be running for a. I'm looking something up right. I never remember case, and somebody's asking me, I had a case sensitivity issue. You know, you got to be careful about things like that. So, like I said, this is the problem with doing things on the fly. Let's see. So, yeah. Okay. All right, we'll have to find out if there's an issue there. Let's do this. The command, if you, by the way, if this causes a problem in your, if you have problems importing, then try installing. If this doesn't work correctly, then you don't have pip installed, and then we will have to find out what the issue is. So let's see, run the cell. Where is the, yeah, somewhere in here is a run the cell command. Where the heck am I not finding it? Hang on. Run the code cells. Ah, idiot. I'm not an idiot. I do sometimes silly things. Okay. No module named Jupiter. Yeah, it figures. That's bizarre. Ah, Jupyter server stopped. That's why. Okay. I didn't start this. All right, let's try this again. New project, virtual end. Users call this project 4. I can clean this up. I want to inherit all my global packages. I want to make available all projects. I use the configured interpreter. My welcome script. Let's put it in a new window. Now I know what Monday's lecture is going to look like. Actually, what I am going to do is, let's see, today is Wednesday. We got a virtual farewell. One of the guys from my company is leaving, which is breaking my heart because he's the most talented young programmer I've ever known in my life. By the end of tomorrow, by the end of Thursday, hopefully today, but more likely by the end of tomorrow, I will post a video of this demo on the YouTube channel, hopefully with sound if I can figure out how I did that wrong. And walk you through this because it's now 13 after 5, and according to my watch, and it's clear I'm not going to be able to finish this. Again, another live demo does spectacularly well, pardon me. So I'm going to wrap up the lecture there. I will take questions if you have them. Obviously, I'll post tonight's lecture on the YouTube channel later tonight, and I will create a new video, as I said, hopefully with sound, that I will post on YouTube, showing some of the uses of pandas and plot9 and hopefully helping out if you've got questions. In the meantime, if you have questions, feel free to continue asking them. Somebody asked if you're permitted to ask me questions on Discord. Absolutely. Send me a DM on Discord. I will get to it as